So if what we're trying to do is optimize a function of several variables, we're going to be looking for places where it reaches a local maximum, places where the function reaches a local minimum, but then not every critical point, not every place where the tangent plane to our graph is horizontal is going to be either a local minimum or a local maximum. And so we're going to have to find sort of a two-step process where the first thing that we do is we locate all the critical points of a function of several variables, and then we go through each of those critical points and ask the question, is this critical point a local maximum, is it a local minimum, or might it be neither one of the two? So first, just to get definitions down, right? A function has a local minimum if the value of the function at that point is less than or equal to the value of the function at every point surrounding it, right? So if my function's value at a point is less than or equal to the value of all the points that are in some nearby disk of xy values around it, then we call that point a local minimum. And conversely, for a local maximum means that the function's value at that point is greater than, strictly greater than the value of all the points in the neighborhoods that surround it. And then if we use the word absolute instead of local, what that means is that this is the largest value that f achieves on its entire domain of definition, whatever that domain happens to be. And then same thing for absolute minimum. So just like in single variable calculus, absolute minimum and maximum points often occur at critical points, which are local minimum or maximum points, but they might not occur at a point that is a local minimum or local maximum. They might occur on the edges of our domain somehow. And so we're going to have to not just look at the critical points, but also look at the edges of our domain. And that's going to be what we do a couple of steps from now once we get there. And so critical points are what play this most important role in the process, right? Critical points are places where every directional derivative of my function is equal to 0. In other words, there is no direction identified by the first derivative, in other words, the gradient. There's no direction that that gradient identifies as the direction of greatest increase. After all, that is the direction of the gradient vector in general, right? The gradient vector points in the direction along which my function is going to increase the most rapidly. And so a critical point is going to be a place where there is no such direction, right? That there is no direction that I can walk that takes me uphill as quickly as possible, at least no direction that the first derivative can see. And so by way of definition, we'll say that a critical point for a function of several variables is a place where all of its partial derivatives are equal to 0 at the same time, right? In other words, that the gradient vector of the function is the 0 vector at that point. And so we've already seen, you've already done a sort of a simple example of finding the critical points of a multivariable function just by taking its partial derivatives, setting each of those partial derivatives equal to 0, and then solving for x and y, right? And I just wanted to sort of quickly, before you get back into your activity here, mention that the example that you did was fairly straightforward because one of the partial derivatives only had an x in it, the other partial derivative only had a y in it. And so to solve that system of two equations, you didn't have to worry about the fact that, the variables might be in both equations at the same time. But in general, we should probably expect that most functions of several variables, when we find their gradient vector, that both the x partial derivative and the y partial derivative, in principle, are going to depend on both the variables x and y. And so very often in the process, we end up with a system of equations that we need to solve to determine where the gradient vector vanishes. So for this function, x squared minus 8xy plus y squared minus 4x plus 4y, when we take its partial derivatives, both the x partial and the y partial have both an x and a y in them. And so for that example, when we set each of those equal to 0, we end up with a system of two equations to solve for x and y. That in this case happens to be a system of two linear equations, so that those of you taking linear algebra with me this summer will recognize some possible ways to solve that. But in general, we should expect that it might not even be a linear system of two equations. It might be, a nonlinear system. We could have y squareds. We could have cosines of x. We could have all kinds of stuff as part of this. And so even just that process of finding the critical points, the process of actually doing the algebra to solve those equations simultaneously can sometimes be a little bit tricky. So I just wanted to put that flag in there before we went into the next piece of the activity. So just to get some practice with that, Let's take a moment and just work on part E of activity 10.7.2 that asks you to find the critical points of the function f of x and y is 2xy minus 4x plus 2y minus 3. So let's take 5, maybe 10 minutes for you to work on finding just the critical points of the function from part E. Then we'll come back and compare notes after that. Great. So you took the partial derivatives of this function and ended up, well, I guess we didn't have to solve a system of equations in this one. But the x partial derivative depended on y only, and the y partial derivative depended on x only. And so when you solve for the critical points here, negative 1, 2 is what you ended up with in this point. Is it negative 1, 2? Yeah, so y equals 2, x equals minus 1. Oh, I see why. Okay. All right. Yeah, that makes sense. Okay, so the next step for us, now that we know kind of how to find critical points, the real interesting question is, how do we tell which critical points might be local maximums, which critical points might be local minimums, and which ones are neither? And so that's going to be the focus of the next activity.